All right, so this Greekcast is going to take you through what pH is, why it's useful to calculate, and why it's useful to be able to determine the pH of a variety of different substances. So let's just dive right in. So pH is basically a measurement scale for acids and bases. It's how you can tell how strong an acid or a base is by what its pH is. So the pH scale, it indicates the acidity or basicity of a solution. It ranges from 0, which is very acidic, all the way up to 14, which would be very basic. So on this end, you're going to have more hydrogen. On this end, you're going to have less hydrogen. So the pH of a solution is defined as the negative log of the hydronium concentration. So you're going to take however much hydrogen is there, the negative log of that, and that is going to tell you what the pH is in numerical value, in numerical form. So it is just the negative log of whatever your hydrogen concentration is. Hydrogen and hydronium are the same thing, so we use them interchangeably, whether it's H plus or it's H3O+. H plus technically doesn't exist in nature, but it exists as H3O+. It's just easier to write it as H+. So a definition of pH, we use these observations to develop kind of our concept of pH. If I add an acid, that means I'm going to add more hydrogen. If I add a base, that means I'm going to add more hydroxide. So that's going to change my pH accordingly. When my hydrogen and my hydroxide concentrations are the same, that when those concentrations are equal, that's when you have a neutral pH. Equal amounts of your acid and your base are present, and so you end up with a pH of 7. So the pH can be calculated if the concentration of either ion is known. So if you know how much hydrogen is in there, or you know how much hydroxide is in there, then I can calculate it. It can be approximated using an indicator, which will change color. Like pH paper is something that'll change color, and then you compare it to a table to see what pH would be what color. Or it can be measured using a pH meter, where the sensor is going to measure an electrical property of the solution that's proportional to the pH. So it's going to tell you how much electricity is traveling through there because of that hydrogen ion, and that is proportional to the pH. So there's 3 ways to really tell what the pH of a solution is. So if you look on here, here's kind of the traditional pH scale. You've probably seen something like this before, where you have a whole bunch of hydrogen, all the way down to where you have a whole bunch of hydroxide, where you have no hydrogen. So what this is showing you is the hydroxide concentration. So as I increase hydroxide, I become less acidic and I become more basic. As I increase the amount of hydrogen, as that number gets higher, then I become less basic and I become more acidic. So things that we associate being very acidic, like hydrochloric acid, stomach acid, lemon juice, pop, tomatoes, coffee, things that we acidic with being more basic, baking soda, ammonia, oven cleaner, sodium hydroxide, laundry detergent is in there. And then kind of the things that are in the middle or more neutral would be your urine and your saliva, distilled water, your blood is more on the basic side, and seawater, kind of in that neutral range, but maybe slightly acidic or slightly basic. So molarity and pH. For a strong acid, when you look at this, for a strong acid, the concentration, this is going to allow you to estimate pH without actually having to calculate it. The concentration of the hydrogen tells you what the pH is. If you look at the exponent here, if I have 1.0 times 10 to the 0, basically if I have 1 molar of hydrogen, that is going to be a very low pH of 0. If I have 0.1 moles of hydrogen, or 1.0 times 10 to the negative third, that is going to be a pH of 1. Times 10 to the negative second is going to be a pH of 2. So you can see it's based on a factor of 10, which is why we use log. Each tenfold change in concentration changes the pH by 1 unit. So as I decrease the amount of hydrogen by 10, I change the pH by 1. And the same thing on the basic side. As I increase the amount of hydroxide, then I increase the pH, or I increase the basicity, or how strong this base is. So this just gives you a little bit of idea of like looking at the concentrations of these things. So the numbers are going to matter, and the exponents are going to matter. So our pH scale, and the neutral pH is a 7. Anything below a 7 is an acid, anything above a 7 is a base. So pH and hydrogen concentration have an inverse relationship. We think of acids as being a low pH but a lot of hydrogen, so high hydrogen. Bases have a high pH but low hydrogen. So that is that inverse relationship. So here's some basic pH equations, and these are the scales that you guys are going to, or the equations that you are going to need. So we're going to do some practice problems. So pH is equal to the negative log of the hydrogen concentration. If I know what this hydrogen concentration is, I just plug it in here, take the negative log of it, and boom, I have the pH. If I know what the pH is, I can figure out what the hydrogen concentration is by doing the anti-log. So 10 to the negative pH power. And then how can I figure out the, if I know what the pH is, how can I figure out what the hydroxide concentration is, or how much hydroxide is there? pH plus pOH must equal 14. They're on that scale. Our pHs go basically from 1 to 14. So if my pH is low, then my pOH would be higher, and they're going to equal, add up to equal 14. So calculating the pH equals negative log of the hydrogen concentration. So this is going to be its molarity. This is going to be its moles per liter, what its actual concentration is. So if the hydrogen concentration is 1 times 10 to the negative 10th, I literally just plug into my calculator negative log of 1 times 10 to the 10th, and I find that my pH is equal to 10. If my hydrogen concentration is 1.8 times 10 to the negative 5th, I just plug that in. I take the negative log of 1.8 times 10 to the negative 5th, and I get a pH of 4.74. In this example, I'm going to calculate what the pH is. Like, this is using a pH meter to tell me what the pH is, and then I can calculate how much hydrogen concentration is there. So if I just take the anti-log of both sides, then I get 10 to the negative pH equals the hydrogen concentration. So if the pH of Coke is 3.12, how much hydrogen is there? So hydrogen equals 10 to the negative 3.12 power, which is 7.6 times 10 to the negative 4th. So that actually tells me how much hydrogen is in that solution by knowing its pH. To find the anti-log on your calculator, look for shift or second function and then the log button. And it should be a 10 to the x. You'll find it that way. So let's do some pH calculations. Solution has a pH of 8.5. What's the molarity of the hydrogen ions? So how much hydrogen is there? So I take 10 to the negative 8.5 power. So the anti-log of negative 8.5 equals the anti-log of the log of the hydrogen concentration, and that's what I end up with. So all I'm doing is just solving for hydrogen instead of solving for pH. So 10 to the negative 8.5, when I plug that into my calculator, I get 3.16 times 10 to the negative 9th. So that amount of hydrogen will produce that pH. Instead of just calculating pH, it's also good to know how to estimate it. So if the starting number is 1, then the pH is equal to the positive value of the exponent. So if my starting number is 1, and you can see in all of these it is, then that exponent, the positive value of that exponent is what my pH is. So here 1.0 times 10 to the negative 5th, my pH is 5. 1.0 times 10 to the negative 8th, my pH would be 8. 1.0 times 10 to the negative 3rd, my pH would be 3. That only works if it's a 1 in the front. So this would be an acid, this would be a base, and this would be an acid. If the starting number in the hydrogen concentration is not 1, the pH value will fall between the positive exponent and one number lower. So if I look at these examples down here, 2.1 times 10 to the negative 5th, well, that is obviously not a 1. So I look at the exponent and one number lower. So my pH is going to be between 4 and 5, which would make it still an acid. 6.82 times 10 to the negative 11th. It's obviously not a 1 for my starting number, so my pH is going to fall between the 11 and one number lower, so it's going to be between 10 and 11. 9.21 times 10 to the negative 7th. My pH is going to fall between 6 and 7. So this one would be a base, and this one would be more on the acid side. So now what I want you to do is actually work through these problems here. So I want you to go through, and I've given you the hydrogen concentration for each one of them. I want you to solve for pH. So you're going to go through and calculate all 4 of these and tell me the pH. Then on these 4, if I tell you the pH, I want you to calculate the hydrogen concentration. So remember, do the anti-log. So 10 to the negative second, or 10 to the negative 5.68, and calculate the hydrogen concentration for each one of those. We're going to go over these in class. So what the heck is POH? Well, since acids and bases are opposites, pH and POH are opposites. POH really doesn't exist, but it's useful when you start talking about bases. In terms of a base, you don't really want to start talking about how much hydrogen it has, because bases don't have very much. So we like to think about bases in terms of hydroxide. So POH just does the same thing that pH does. You're just looking at it from the perspective of the hydroxide concentration instead of the hydrogen concentration. So POH equals negative log of hydroxide. And since pH and POH are on opposite ends, they must add to always equal 14, because that's our pH range. So looking at this, pH goes from 0 to 14. We look at our hydrogen concentrations going from anywhere from 1 to anything with an exponent of 10 to the negative 14th. Hydroxide would go from 10 to the negative 14th up to 1. That would make it more of a base because it would have a higher amount of it. This would make it more of an acid because it would be the higher amount on the one end. And then POH going from 0 to 14, it's going to be opposite. So something that's an acid is not going to have much hydroxide. It's going to have a lot more hydrogen. And remember, hydrogen and pH are inverses of each other. So this is just another scale to look at to be able to interpret the difference between these two opposite things. You can use any one of these values to calculate any of the other values using our equations. So if my pH is 1, what is my POH? And remember, pH plus POH must equal 14. If my POH is 12, what does the pH have to be? If the pH is this, what does the POH have to be? So go ahead and solve those 4 problems, and we'll go over them in class. Here is another diagram that looks kind of busy and confusing, but it's actually pretty easy to understand once you start following the arrows. So how do we convert from pH to hydrogen concentration? To go from pH to hydrogen concentration, you take 10 to the negative pH. To go from hydrogen concentration to pH, you use the negative log of the hydrogen concentration. So you just follow the arrow and see what it is you're calculating. You can go from hydrogen concentration to hydroxide. You can go from hydroxide to POH. You can go from POH to pH. This is just another table that'll kind of tell you what equation to use as you are making the transition from one to the other. So what's the importance of pH? Why do we study pH so many times? pH is important in terms of agriculture. You grow crops best in the soil with proper pH. If your tomatoes don't grow very well, you need to check the pH of your soil and make sure it's not too acidic or too basic. Your physiology, your blood, must maintain a very specific pH, and even a shift of 1 is often fatal. So your body must maintain pH of all of your body fluids. Acid rain lowers the pH of water in aquatic systems, causing problems for native fish, as well as native plants. The municipal services, our sewage treatment and our water purification require optimal pH. They have to make sure the pH is right for the water coming out of your tap. And then in industry, many processes require strict pH control for cost-effective production. Things need to be done at an acidic level or at a basic level or in a way that's going to, make sure and kill bacteria or kill viruses. So there's a lot of important uses for pH. Another one that's not on here would be your fish tanks, your own personal fish tanks at home or your own personal pools at home, making sure that they're not going to hurt somebody, that they're at the optimal levels that they need to be. So go ahead and work through the practice problems. We will finish them and go through them in class, and you will do more practice problems with pH and POH and hydrogen concentration.